All right, in this lesson, we're going to be graphing radical functions, which includes our square root function and cube root functions. And so for square root, let's look at the parent function, which is just f of x equals square root of x. And so to get some good points to graph, we can just plug in different x values. Probably want to pick perfect squares to get whole numbers. And so square root of 0 would give us 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. And so we have the point 0, 0, 1, 1, and then 4, 2, and then 9, 3, and then 16, 4 doesn't fit on the graph. And so our function looks something like this. And then we can't plug in negatives to a square root because square root of negative isn't going to be real. And so we also can't get negative outputs. And so square root of anything can't equal negative. And so that's why we don't have anything over here or down here. And so the square root parent function stays in the first quadrant. And so he has this blunt stopping point, which we call the starting point, and it's at 0, 0. And so when we graph other square root functions, we want to figure out what the starting point is if we transform this by shifting it left, right, or reflect it. And so keeping track of this point will be very helpful. And then because the starting point is at 0, 0, that's its x-intercept and the y-intercept. Because he has this blunt starting point, stopping point, there's no symmetry. The domain of this function goes from 0 to infinity, and we use a bracket because 0 can be included. And then same with the range. It's going from 0 to infinity. Starting at 0 on the y and then going up forever. And then for the x, we're starting at 0 on the x-axis and going to the right forever. And so this starting point is a minimum for the function, and that value is 0. You always pick the y value. For the cube root function, this one's different because we can now plug in negative x values and we can also get negative output values. And so the cube root of negative 8 would be negative 2. Cube root of negative 1 is negative 1. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of 8 is 2. And so we still have the point 0, 0, and 1, 1, but then we skip all the way to 8, 2. And so it kind of looks like a flatter square root, but now we have the negatives. And so negative 1, and negative 8, negative 2. And so you're probably seeing some symmetry for the cube root function. It kind of looks like two square root functions, just one is reflected. And so we call this point the inflection point. Because it's where it's opening to the right, and then in the bottom half, it's opening to the left. So anytime a function changes its direction of opening in the middle, that's called inflection. And so this particular inflection point is 0, 0. And just like with square root, that means his x-intercept and y-intercept is 0, 0. And then the symmetry point, there's point symmetry or rotational symmetry, which you may remember from geometry. And it's about the inflection point. So the inflection point will always be the point of symmetry. And then the domain for cube root is all real numbers. It goes forever to the left and forever to the right. And same with the range. It's going forever up and forever down. And so whenever you're dealing with cube root, all real numbers, kind of like linear. And so there is no max or min, so you can say D and E or none does not exist or none. And so to graph other square root and cube root equations, we're just going to transform the parent. And so whenever you see a value being multiplied in front, that's called a vertical stretch or a vertical compression. And then it's also a reflection over the x-axis. And so, for example, if a is negative, it's going to be, our square root would be reflected upside down. If you have a number being multiplied inside the radical, that is going to be a horizontal stretch or horizontal compression, or a reflection across the y-axis if that b value is less than 0. And so for our square root, that would be reflected across the y-axis. It would look like this. And then inside the parentheses, if you're subtracting, that's going to move right h units. And then the value outside the parentheses or outside the radical is going to move you up k units. And so if k is negative, it could be down. And then if you had an x plus h, that would move you left. Okay, and so for these next examples, we're going to write what the transformations are, and then we're going to use our parent function to be able to graph. So starting with number 1, this is square root. And so we can picture our square root parent function. It goes 1, 1, 4, 2, and then 9, 3. And so the transformations is right 2 and then down 4. And so we can take our square root parent function and just move him right 2, down 4. And that would be our new graph. His new starting point would be 2, -4. And so you could start by just graphing that point and then following the pattern over 1, up 1, over 3, up 1, over 5, up 1. Next, we have cube root. And so we can picture our cube root parent function, which goes 1 and then 8, 2 on each side. He's got the symmetry going for him. So up to the right, I'm gonna do better. And then down to the left. And so this graph has been vertically stretched by 3 and then left 2. And so we know that's going to move the inflection point just to the left 2 units, so it's now at -2, 0. And then usually we go up 1 over 1, but that vertical stretch by 3 is going to cause us to go up 3 over 1. And then our next point is 7 units away, and so we can go up 3 more, and then 7 units to the right. And then we can do the same thing going down. So down 3 over 1, down 3 over 7. And so up to the right from the inflection point, kind of like square root, and then down to the left. Okay, and so here we're dealing with square root. Be careful, that is a vertical stretch by 3. That is not the index of the radical. That is not a cube root. And so we have 1 two transformations. The negative is a reflection across the x-axis, and so we know our square root is now upside down, and then he's also been vertically stretched by 3. And so because he hasn't been moved left or right, that starting point is still 0, 0. And so our starting point is 0, 0. And because he's still going to the right, still facing to the right, the domain is 0 with a bracket to infinity. And then the range starts at 0, but it's going down. And so it's going from negative infinity to 0 with the bracket. And then because he's still at 0, 0, that's still going to be your x-intercept and y-intercept. And so to graph it, we have 0, 0 as the starting point. And then usually he goes over 1, down, well, up 1 over 1, and then up 1 more over 3, up 1 over 5. But he's now upside down. And so that would take these points below the x-axis. And then to do the vertical stretch by 3, our y distances, instead of being 1 each time, they're going to be 3. So I'm going to get rid of these points. So we're going to go down 3 over 1, down 3 over 3, down 3 over 5. Right? And then this last one is cube root. That is a small 3 in the radical. And so we have 1, 2 transformations. The index of the radical is not a transformation. And so this cube root has been reflected over the x-axis and then up 6. That plus is not under the radical. Otherwise, if this radical was longer, this would be left 6. But it's outside the radical, so up 6. And so that puts our starting point up 6. So usually it's at 0, 0, not our starting point, our inflection point. So up 6 units would be here. And so our parent function usually has 1 on each side, but because he's been reflected, kind of like a linear function, the slope will now be negative between those 3 points. Okay. And so since it says 3 points, you could leave it like this and just go up to the left. But I always like some extra points, so I go up 1 over 7 for another point. And then same on the other side, but down 1 over 7. And so you can make your S shape that way. And so the inflection point is 0, 6. And then the domain and range for cube root, kind of like linear. You never have to think about them. All real numbers all the time for both. And then the x-intercept is actually going to be harder to find because it's going to be way over here. This function is going to keep going down. And so we may need to calculate that algebraically. The y-intercept is on our graph. It's 0, 6. And so to find the x-intercept, you need to set the equation equal to 0. It's when the y value is 0. So you put 0 in for the f of x term. And so isolate the radical. You get negative cube root of x equals negative 6. Technically, this is a negative 1 that we need to divide by. So cube root of x equals positive 6. And then we can cube both sides. And so x equals 216. And so that would not show up on our graph. So 216, comma 0 for the x-intercept.